Okay, let's look at assignment 4, which is designed to simulate the exam. And I should point out at this point as well that the exam has a practice exam with full work solutions available as well. But the way it's structured is a series of problems, a few more than presented here, where you're given scenarios and data sets, and you have to, with questions attached, and you have to work out the answers to the questions based on the data set. Each one should be fairly obvious to you when you come to it, what sort of analysis it's looking for, but generally that's hinted in the question as well, or the scenario. There'll be warm-up ones to do with finding the mean and standard deviation to get you rolling. And then there'll be some more complicated, but not overly complicated, statistical analyses to do, like t-tests, hypothesis testing. They'll be based around hypothesis testing, so setting a null and alternate hypothesis, coming up with a test statistic. What's the probability of that test statistic based on the data? What's the is that p-value significant or not? But we'll go through the strategies for assignment 4. I'll go through the complete question 1 and do a little part of each of the following questions as well. But these mimic pretty closely the exam. It's just a little bit short. Let's see this first one. Classic question where the scenario is full of a little bit of guff, but when you break it down, it's just a question about 2 samples that are taken. This one's based around a data set we've used quite a lot. Melbourne Cup winning times, where we have the year of the race in column A, the age of the horse in column B, and the winning time for that year in seconds. Now, the crux of this question is, are the winning times quicker now compared to 150 years ago, so the first 20 running? So are the most recent 20 winning times quicker than the earliest 20 winning times? Now you could do this a couple of different ways. One would be working out a confidence interval for the difference in the 2 samples, and if that confidence interval includes 0, then they would be significantly different. Or we could just use the t-test formula. I'll show both of them now. So the first thing that I'll do is I'll just neatly come up with the mean and standard deviation for these 2 data sets. First 20, last 20, get the average for each. Now in the exam you will be told that all data should have no decimal places at all. So I'm just going to correct this first column to have no decimal places. Let me do that. This one here. There we go. And so all numbers followed during the analysis should have no decimal places as well. Standard deviation. Now I'll see all you're working out, but as a rule just remove the decimal places as you go. So we've got the mean and standard deviation for these 2 data sets. Then we want to know if they're significantly different. So the first way I'll do it is the confidence interval way. So we look at the 25%, 95%, or 99%, or the confidence level that we're looking for. This one doesn't specify, so we'll go for 95% confidence interval for the difference. And if this confidence interval includes 0, that means they're not significantly different. That's because if the means were the same, then if you subtracted one from the other, you get 0. So if we're not sure that the true mean difference isn't 0, then we can't say that they're definitely different. So we'll start just doing the hypothesis testing steps and then look at the 2 different methods first. Alright, so Step 1 is state a null and alternate hypothesis. Null hypothesis is mean 1, let's call it x1 equals x2. And the alternate hypothesis, so the null hypothesis, or HO or H no difference, is always has an equal sign in it. The alternate is, if we reject the null hypothesis, what are we asking? Well, we want to know, is the times in the first 20 years greater than the times in the most recent 20 years? So x1 is greater than x2, longer time. Then we normally do steps 2 and 3. Step 2 is determining a test statistic. And then step 3 is that test statistic significant. When we're using computer software, step 2 and step 3 are generally together. Let's doing that as a year. Call it step 2 and 3. There we go. Step 1. So we want to work out let's do the t-test way now. What is the probability of the null hypothesis? We do a simple t-test here, equals, and we'll look at some of the theory very quickly behind this. Array 1, array 2, number of tails is 1, because we're only interested in, is x1 greater than x2? We're not looking at, is x1 just different to x2? In other words, is it the first 20 years of winning time is smaller, significantly smaller, or significantly larger? We just want to know if it's significantly larger, so it's one-tailed. And then it's not paired data, it's two sampled data, and we always go number 3 for that unequal variance. And there we're given a p-value. That is the probability of the null hypothesis occurring based on the two samples. The null hypothesis being the mean of 1 is the mean of 2. The true mean of sample 1 and the true mean of sample 2 are the same. That's actually 1.3 times 10 to the negative 13, which is 0.0.0023, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 3. So extraordinarily small. If we're looking at the 95% level, where we want to know, would, in 95% of the time, if we took these random samples, would the sample means be within the same area, or would they be the 5% of the time outside that area? Or what is the probability, is, if with 95% confidence, is the probability that they're not the same, that they are the same, sorry, 5% or greater? Is the probability that they're the same 5% or greater? We're given here that the probability of them being the same is 0.0000013%. So the probability that they're the same is a lot less than 5%. So we do that in step 4. The p-value is less than 0.05. So the probability of the null hypothesis being correct is less than 5%. Therefore, we reject the null hypothesis and accept the alternate hypothesis. And then step 5, we just put it into real world terms. Therefore, horses have got quicker in the last 150 years. Have got significantly quicker. If we did this the 95% confidence interval way, we have to use the formula where first of all we subtract the two means, so equals one mean minus the other mean, and that gives us the average difference between the two, and then we need a margin either side of this. So actually I'll put xd equals that minus that. And then the margin is t times the square root of S1 squared divided by N1 plus S2 squared divided by N2. T we get from the T table, where we use the degrees of freedom from the smaller sample size. So our sample size is n equals 20, so our degrees of freedom are 19. We go to the table and find, with 95% confidence, what is T, to give a 95% confidence interval, what is T for degrees of freedom 19. Then we multiply that by the square root of S1 squared divided by N1 plus S2 squared divided by N2. We add that, we do our upper confidence level is xd plus m, our lower confidence level is xd minus m. If that confidence interval braced by the lower confidence level and the upper confidence level includes 0, then we say they're not significantly different. So let's a little bit remind ourselves of the theory of that. If I do a quick histogram of the data here for the first 20 years, and I'll put it in here so we can see it. There's the data, then we'll make a graph of that. There we have it. So there we have the histogram of the winning times of the first 20 years, and I'll just put a trend line over that. From memory, it's not a very awe-inspiring trend line, but it is all the same, a trend line. So there's the beginnings of a nice even distribution where it rises in the middle and down on the outside. 95% of data, according to the T distribution, if this is normally distributed, will be the sample mean plus or minus T times the standard error, which is the standard deviation of that sample divided by the square root of the sample size. Right, so 95% of values in this distribution here, because it is normally distributed, will be plus or minus T from the T table times the standard error. Now, if this was a perfect normal distribution and we're using the true mean and the population standard deviation, 95% of values will be plus or minus 2 times the standard deviation. But because we're using samples and we don't have the population standard deviation, we can't multiply by 2, we have to multiply by T, which would be close to 2, but probably a bit more than that, more than 2. We don't use the standard deviation, we use the standard error, because we're looking at a sample. So this question is asking, alright, we're asking, is the most recent 20 years somewhere down here in the extreme lower end? And more exactly, are they in the bottom 5% of this distribution? If the sample mean of the most recent 20 years are in the bottom 5% of this distribution, we say that the distributions are most probably different, or the sample mean is significantly different to the first 20 years. All right, so let's try and think about it as this distribution. Where does the other sample mean lie on this distribution? If it lies in the extreme end, then we say it's significantly different. If we're just wondering if it's greater or smaller than, then the sample mean has to be in the bottom 2.5% on this end, or the top 2.5% on this end, because the middle section includes the 95%. That would be for a two-tailed one. Because we only care about the bottom 5%, it's a one-tailed one. If we wanted to know if the most recent 20 years were significantly slower, or the times were greater, we'd be looking at, does the sample mean lie up here? Let's go to the next question. The next question is very similar to that first one. It's got looking at Mark Taylor's cricket scores. And did he score more runs in the first innings compared to the second innings? And it says exclude matches where he didn't score any runs in the second innings, like this one here. We have no value there. So first of all, we get rid of those cells, those rows. Another way we could do it is by sorting the table, but I'll just delete them. Make sure we don't include them. And again, in this case, all we're really looking at, if we just forget about the whole Mark Taylor thing, we're asking, is one sample mean significantly greater than the other sample mean? Is his average first inning score significantly greater than his second inning score? So first of all, we'll set a null hypothesis. HO x1 equals x2. Alternate hypotheses, x1 is greater than x2. First innings mean is significantly greater than the second innings mean. Step 2 and 3, do the t-test. Now again, we can get Excel to do it for us. This time, we don't have unpaired data, we've got paired data because we're comparing one score to another in the same match. So we put array 1 in here. And again, we could do this the confidence interval way as well. Some people prefer that. But this is pretty simple. It's a one-tailed test because we only care about greater than. So if the alternate hypothesis doesn't have a doesn't equal sign, the equal sign with the cross rule, it's got a greater than or less than, that means it's one-tailed. And then here we put in a 1 because they're paired samples. So this gives us the probability, this is the p-value, the probability that the null hypothesis is correct. And in this case, it's 0.289. It hasn't given us a confidence interval to run on, so we'll use the threshold p-value as 0.05. So we have to be 95% confident that the two means are different. And to be 95% confident that the two means are different, the p-value has to be 0.05 or less. P-value is greater than 0.05, therefore we accept the null hypothesis. Right, we don't have enough evidence to reject it. The probability that they're the same is too high to reject it, therefore we accept it. Therefore Mark Taylor did not score significantly more runs in the second innings. Now I was just going to give you a hint as how to work that one out, and I've just done it for you, so there you go. Question 3 is a little trickier. This is looking at regressions. So what we're doing is we're asking, can variation in one variable explain variation in the other variable? Is there an association between two variables? In this case, it's the year of the Olympics, years greater than 1900. So -4 would be 1896, 96 would be 1996. We're asking, is there a significant association? So can you predict in a confident manner the distance, say, jumped in the long jump based purely on the year that the Olympics were held? And we do this via regression analysis. So let's have a look at how we do it. First of all, we generate a scatter plot. In this first one, I'm going to do long jump versus the year. Then you'll have to do discus throw versus year and high jump versus year. So is the year that the Olympics were held associated to how far they jumped? So we highlight the two. And I should point out, the question asks you to convert these measurements into centimetres from inches. And then we have the scatter plot. We have the year in the y-axis and the distance in the x-axis. Now the problem with this, as described in topic 8, is we put the explanatory variable in the x-axis and the response variable in the y-axis. In this case, we're trying to predict whether or not the year the Olympics was held determined the length they jumped. So the explanatory variable would actually be the year, so it should be in the x-axis. So the way we get around that, and I'm sure there's trickier ways, is I'll just go over here, convert my inches to centimetres, and I don't quite know what the conversion is. I'll just do it off the top of my head, 2.8, something like that. I'll get rid of those decimal places. And then I'll do this regression again. We have the columns in a different order. And there we go, we have now the proper order. We've got the year in the x-axis and the response variable in the y-axis, distance. I add a trend line and go, I want the equation and I want the r squared. The r squared is telling us how much variation in the x variable, so the year, how much does the variation in that variable explain variation in the other variable. So essentially, how well can we predict the y variable based on the x variable? And we can read it as a percentage. So what this r squared is telling us is that 80.44% of the variation in the y variable can be explained by the x. Right, so there's 20% of the variation in distance jumped each year is explained by something other than the year. Right, so that's pretty strong. That's an amazingly strong relationship between distance and year held. The equation tells us how much extra distance did the jumpers achieve each year. That's this number before the x. That's the slope of this line. This equation is the equation for this line. The number before the x is the slope of the line. The number at the end there, 780.58, is where that line meets the y-axis. It meets it with y equals 780.58. So if we just substitute in any number for x, we'll get the distance that is predicted based on this model for that year. So we can r squared r. R is just r squared, the square root of r squared. So we just go square root of 0.8044, and it's 0.896883. It's the correlation coefficient. It tells us how strong the association is. And we use rules of thumb with this. Greater than 0.9 is a very strong association between the two variables. Greater than 0.75 is a strong one. So this looks like a very strong relationship. But we can actually go to Pearson's R table and find out whether or not this is significant. Is there a significant correlation between the two? What Pearson's R table, which is in your tables booklet, what that gives you is for any particular sample size, what is the minimum value of R you need for there to be a significant correlation. So here we'd use a sample size of 20 because there's 20 measurements. We'd go to 20 on the table, then work across, just like the t-table, until we find the level of confidence we're after. We want to be, say, 95% confident that there's a significant relationship, and it will tell you that R has to be around 0.45. Because our R value is greater than 0.5, we'd say there's a statistically significant correlation between these two variables at the 95% confidence level. The final one is the easiest of them all. This is just getting you to calculate a test statistic and working out what is the probability of getting that test statistic. So what it's telling you here is a textbook claims that the true mean average time between nerve pulses is 10.1 seconds. 10.1. You have a sample mean that you've calculated that you're going to test the true mean against. 10.95. Our sample also has a standard deviation. Note you're not given a standard deviation. If we were given a standard deviation, we'd calculate a Z-score, but because we're not, we have to calculate a T-score. All right, so we have a true mean, it's given to us. We have a sample mean 10.95, and we have a sample standard deviation. So we use a 5-step hypothesis test to work out whether or not the textbook is correct based on our sample. First of all, we have to state the null and alternate hypothesis. Null hypothesis is true mean equals 10.1. Alternate, is it two-sided, two-tailed? No, true mean is greater than the weighted average. So the true mean is greater than 10.1. Next we have to calculate a test statistic. Because we're not given the population standard deviation, we calculate a t-score. And we use that, I'll just put sample size here, 799, degrees of freedom, 798. So we can calculate the t-score for 95% confidence by going to the t-table, finding that 798 degrees of freedom, or the closest number to it, in the left column, and working across till we find the desired confidence level, and that is our value of t. No, that's completely wrong. No, first of all, we calculate the t-score, pardon me. So we calculate the t-score by doing our sample mean. I'll just click on it there. Minus equals sample mean minus the true mean divided by standard deviation divided by the square root of the sample size. Just got a bit ahead of myself before. So t is 2.3. If we're given the population standard deviation, then we calculate a z-score. Okay, and we use the z-table to work out the significance of it, but we're using a t-table. So it's essentially asking how many standard deviations is that true mean from the sample mean. So 2.3, then we can find the probability of getting that t-score using the t-table by going to the degrees of freedom and working across until we find the probability, until we find where 2.3 is on it. And you'd find that it's between 0.2 and 0.1. So the probability of getting that t-score with that sample size is between 0.02 and 0.01, right, between 1 and 2%. That's using the t-table. So have a go at that. We can get Excel to do it for us by doing the t-dist formula, selecting our t value, getting the degrees of freedom, and the number of tails is 1. And that gives us the exact probability of that t-score based on this sample. And it's 0.010844. So are we confident that the true mean is greater than the stated based on the data? So is it greater than 10.1? Well, yes, we would, because the probability of our null hypothesis being correct is only 1%, or 0.010844. So with I should say the true mean is greater than 10.1 with 95% confidence. However, it also asks, are we confident at the 99% level? Well, at the 99% level, we need the p-value to be less than 0.01, but it's not, it's greater than 0.01. So the other part of the question is, true mean is greater, is not significantly different to 10.1 with 99% confidence. So at 95% confidence, we need our p-value to be less than 0.05 for there to be a significant difference. With 99% confidence, we need our p-value to be less than 0.01 for there to be a significant difference. Therefore, we'd reject the null hypothesis at the 95% confidence level, but we would accept it at the 99% confidence level because our p-value is greater than 0.01.